What are acids and bases? Let's find out. We're going to start with one of the earlier theories, Arrhenius' theory. Arrhenius' theory says that acids release hydrogen ions when dissolved in water. So what this looks like is it's the dissociation of the acid. So if we have HCl and we put that HCl into water, it's going to allow our hydrogen ions to be released and our chlorine, I did that again, our chlorine ions as well. And then so now that they're in their ions, ion form, they can undergo the chemical reactions that acids and bases do. Bases release hydroxide ions when dissolved in water. So if we have sodium hydroxide and we put that into water, we get sodium ions and hydroxide ions. And this is that basic net ionic equation for these neutralizations, because you have the hydrogen ions and the hydroxide ions that form water, and then you have the other ions that make the salt. And so Arrhenius' theory helps understand why bases and acids can neutralize each other. However, Arrhenius' theory was limited and inaccurate because in the acids category, we don't actually release protons, H+. What actually happens is water participates in that reaction and we get H3O+, which I'll talk about in a little bit. Bases were very narrow, and that's the weakest part of Arrhenius' theory. He said bases have to have the hydroxyl groups. But as we have learned, there are other types of bases, especially organic bases with the nitrogen, that do not release those hydroxyl groups necessarily, or don't require the hydroxyl group within the compound in order to be a base. The Bronsted-Lowry definition or theory builds on Arrhenius's, but opens up the door for more types of bases and helps us understand how water is actually involved in this process. The theory is still that acid is a proton donor. It is going to have that H that it can give up. That did not change from Arrhenius. However, the bases became more broad. Bases are proton acceptors. What this means is there's a lone electron pair that can accept the hydrogen ion. Looking at our example below, here we have hydrochloric acid. So if we have an acid and it's going to donate a proton, it has to donate it to a base. And it's going to donate it to something that has lone electron pairs. Well, lucky for water, water has those lone electron pairs. So when HCl dissociates into water, that proton gets accepted by one of those lone pairs of electrons on oxygen, and it forms what's called the hydronium ion, or heavy water. The hydronium ion is that proton that the Arrhenius acid definition has stated, but it's actually in the form of hydronium. And then we have the chlorine ion floating around in there as necessary. So in this dissociation, water is acting as that base, accepting that proton. So this definition of proton acceptors opens up a wide avenue of what can actually act as a base, and it opened up the door to our organic or nitrogen-based compounds that have that lone electron pair. Now, looking at this definition of an acid, both Arrhenius and Bronsted-Lowry said that acids have to have a hydrogen to donate. But there's different levels of these acids, and it's based on how many hydrogens are associated with the anion it's bonded to. Monoprotic acids, mono means one, protic means proton. So it has one hydrogen in which it's going to dissociate or donate to the base. Diprotic is 2, so there's going to be 2 protons in which it can donate. Triprotic is 3, so it's going to have 3. And so based off these different levels, we can make more predictions about how these acids are going to interact with bases. The last category of acids is what we call amphoteric species. So an amphoteric species is actually a compound that can act as an acid or a base, which means that it has a hydrogen to donate and it has lone electron pairs in which it can accept. Water is the most common amphoteric species because if you have HCl plus water, and I'm going to do HOH so we can see those lone electron pairs, HCl is going to act as the acid because it has a proton to donate. So it's going to donate that proton to water, which means water is going to act as our base to give us our hydronium ion and then the chlorine ion. However, if we have NH3, a very common simple inorganic base, it has a lone electron pair on that nitrogen because nitrogen always makes 3 bonds and 1 lone pair in its neutral form. If we put ammonium into water, that is going to be our base. Water has a proton in which it can donate. So water is going to act as the acid, and it's going to donate a proton to that nitrogen because that nitrogen is going to have a preferential reach to those hydrogens over that oxygen. So when this happens, that nitrogen compound makes an ammonium ion, so this is where ammonium comes from, and it's going to release a hydroxide ion. And so there is where that Arrhenius theory is with that hydroxide ion. He was not wrong in the fact that hydroxide is present. It's just how do we get to that hydroxide? So our nitrogen-based bases release hydroxide ions without having the hydroxide itself because of how it interacts with water, which is amphoteric. There are different species. As long as it has that lone electron pair and a hydrogen, we can then use those to help understand properties of acids and bases and how solutions are going to interact.